Let's take a reaction where A plus B gives us our products, and the lowercase a and the lowercase b represent the coefficients for our balanced equation. It makes sense that if we increase the concentration of A and B, right, A and B would be closer together in space and more likely to react, therefore increasing the rate of our reaction. And this is true for most reactions. If you increase the concentration of your reactants, you increase the rate of your reaction. We can check this by doing some experiments. So let's say we want to figure out what the effect of the concentration of A has on our rate of our reaction. So we're going to hold the concentration of B constant. So we hold the concentration of B constant in our experiments. We change the concentration of A, and we see what effect that has on the rate of our reaction. We're going to use the initial rate of the reaction, and that's because as our reaction proceeds, the concentration of products will increase. And since reactions are reversible, if we have some products present, right, that can affect the rate of our reaction. And that's not our goal. Our goal is to figure out what effect the concentration of our reactants has on our rate. And so we use the initial rate, where we have only reactants present and no products. So in our first experiment, let's say the concentration of A is 1 molar, and the rate of our reaction, the initial rate of our reaction, is 0.01 molar per second. And in our second experiment, we increase the concentration of A to 2 molar. We hold the concentration of B constant, and we observe the rate of our reaction to increase to 0.02 molar per second. So we've increased the concentration of A by a factor of 2. And what happened to our rate? Our rate went from 0.01 to 0.02. So the rate increased by 2 as well. All right, let's compare our first experiment with our third experiment now. We're going from a concentration of A of 1 to a concentration of A of 3. So we've increased the concentration of A by a factor of 3. And what happened to the rate? The rate went from 0.01 to 0.03, so the rate increased by a factor of 3. All right, to figure out the relationship, you have to think to yourself, 2 to what power x is equal to 2? Obviously, that would be 2 to the first. 2 to the first is equal to 2. Right, we could have done it for our other comparison as well. 3 to what power x is equal to 3. Obviously, 3 to the first is equal to 3. So the rate of our reaction is proportional to, that's what this funny symbol means here, the rate of our reaction is proportional to the concentration of A to the first power. All right, let's do the same thing for the concentration of B. So we do some experiments where we change the concentration of B, and we see what effect that has on our initial rate. So for all of these, we're going to hold the concentration of A constant. Therefore, whatever we do to B is reflected in the rate of our reaction. So in our first experiment, the concentration of B is 1 molar, and the rate is 0.01 molar per second. And then we change the concentration of B to 2 molar, right? We double the concentration of B while holding the concentration of A constant. And we observe the initial rate of our reaction to be 0.04 molar per second. So we've increased the concentration of B, not A, let me change that. We've increased the concentration of B by a factor of 2. We've gone from 1 molar to 2 molar. And what happened to the rate? The rate went from 0.01 to 0.04. So we've increased the rate by a factor of 4. Let's compare our first experiment with our third experiment now. We're going from a concentration of B of 1 molar to 3 molar. So we've increased the concentration of B by a factor of 3. And what happens to the rate? The rate goes from 0.01 to 0.09. So we've increased the rate by a factor of 9. So now we think to ourselves, 2 to what power, I'll make it y, 2 to what power is equal to 4? Obviously, y would be equal to 2. 2 to the second power is equal to 4. Or 3 to what power y is equal to 9? Obviously, 3 to the second power is equal to 9. So we've determined that the rate of our reaction right, is proportional to the concentration of B to the second power. All right, now we can put those together. We can put these together to write what's called a rate law. Okay, so we know that the rate of our reaction is proportional to the concentration of A to the first power, and we know that our rate is proportional to the concentration of B to the second power. And then we put in what's called a rate constant here, K, and this represents our rate law. So let's go through these one by one here. So capital R is the rate of our reaction, right? This is the rate of our reaction, right? K is what's called the rate constant. So this is the rate constant. And there's a difference between the rate of our reaction and the rate constant. If we change the concentration of our reactants, we change the rate of our reaction. But if we change the concentration of our reactants, we don't change the rate constant, right? This is constant. It does depend on the temperature though, so we'll talk about that in later videos. Here we have that the reaction is concentration of A to the first power. We say the reaction is first order in A. So we say that our reaction is first order in A. And we found that it's second order in B, right? So we had a 2 here. So this is second order in B. And we can also talk about the overall order of our reaction. So for first order in A, right, we're first order in A and second order in B, the overall order would be 1 plus 2, which is equal to 3. So the overall order of our reaction is 3. All right, let's go back up here to the general reaction that we started with, right? So let's go right back up to here. We have this, and let's write a general rate law. So if this is your reaction, your general rate law would be R is equal to your rate constant, right, times the concentration of A to some power, I'll make it X, times the concentration of B to some power, which I will make Y. And the reason why I'm showing you this is to show you that you can't just take your coefficients, right? You can't take your coefficients and stick them into here, right? So it doesn't work that way. You'd have to know the mechanism of your reaction. So these orders have to be determined experimentally. So you have to look at your experimental data here. And the orders affect the units for your rate constant. For example, let's go back down to here and let's figure out the units for the rate constant for this example. So the rate of our reaction, right, the rate of our reaction was in molar per second, right? This is molar per second. We're trying to find the units for K. The units for concentration are molar, right? So this would be molar, and then this would be to the first power. And this would be molar to the second power. So we'd have molar to the second power. All right, so solving for K, right, you could just go ahead and cancel out one of these molars right here and solve for K. So you would get, this would be 1 over seconds now on the left. So 1 over seconds, right, and divide by molar squared. So 1 over seconds times molar squared. Or you could write this 1 over molar squared times seconds. So those would be your units for K for this reaction, right, with an overall order of 3. But it can change, right? It can change depending on the order. Now let's look at this reaction. We have only one reactant, A, turning into our products. And if we look at the two experiments, in our first experiment, the concentration of A is 1 molar, and the initial rate of reaction is 0.01 molar per second. If we double the concentration of A to 2 molar, the rate stays the same. It's still 0.01 molar per second. So even though the concentration of A is going from 1 molar to 2 molar, right, that's doubling the concentration or increasing the concentration of A by a factor of 2, the rate stays the same. So you could say the rate, it's the rate times 1 because it's the same rate. So 2, right, so 2 to what power x? 2 to what power x is equal to 1. Obviously, x would have to be equal to 0. 2 to the 0 power is equal to 1. So any number to the 0 power is equal to 1. So this reaction is zero order. It's zero order in A. And if we wanted to write our rate law, we would write the rate of a reaction is equal to the rate constant K times the concentration of A. We have only one reactant here. And since this is zero order in A, right, we could just write the rate of the reaction is equal to the rate constant K. And so if you wanted to know the units for the rate constant K, well, the rate is in molar per second, and so those would also be your units for K. K would be in molar per second. So here's an example of how your units for K change depending on the overall order of your reaction.